Okay, well, hello everybody. As he mentioned, my name is Maria Frischman, and I'm here to talk to you about my master's thesis project. I'm developing an automated model. Oh, hold on, I forgot. Sorry. I'm developing an automated model to identify barrier island features from LiDAR data, and this work is done under the direction of Dr. Joanne Halls. So, barrier islands are environmentally vulnerable, they are economically valuable, and they're also extremely dynamic. And so understanding how these barrier islands are changing over time is very important to coastal management and development planning. So a barrier island is just a sandy linear land feature that parallels the coastline, and it protects the mainland from the open ocean. A typical barrier island is composed of beach, followed by a dune ridge, and some back barrier, and some marsh. So for my project, what we wanted to do is we wanted to segment the individual features of the barrier island to identify how these features are changing over time. Instead of looking at how the entire barrier island is moving, we wanted to see how the different features of the barrier island are changing over time. So we segment the barrier island into 8 distinct features that we then map using LiDAR data and then look at change over time. So we identify the intertidal zone, which is the zone of the barrier island that is affected by tides on a daily basis. The supertidal zone is the portion of the barrier island which is only impacted by tides during astronomically high tide periods. The dune portion, the hummocks, which are either relic dunes or baby dunes. Swales, which are the portions of the low regions of a barrier island that are between the dune lines. Channels, which are cut by water and run between the dune lines. And overwash fans. And overwash fans are basically sediment from the front part of the island that has been moved to the back side of the island. We will also separate water, and on developed barrier islands, we will be segmenting the structures as well. So the only geospatial data that this project uses is LiDAR data. LiDAR, which stands for light detection and ranging, is an active remote sensor. Essentially, the sensor emits a beam of light which travels down to the Earth's surface, is reflected by the Earth's surface, and is sent back to the sensor. The sensor does not only record the reflectance properties of the surface, but it also records the amount of time that it takes for that light beam to travel down to the surface and return back to the sensor. That time, in combination with the GPS data that is recorded, is then converted into an elevation data. So the LiDAR's primary objective is to collect elevation of the surface over which it's flying. So the sensor has the system has 2 components: a platform which is flown over the Earth's surface, and then the sensor that is detecting the system. And the sensor is made up of a laser, a high precision clock which times the time that it takes for that light beam to travel, a GPS, internal navigation which records the position of the platform that is flying, and then the ground GPS station which is used to make any corrections to improve the accuracy of the GPS system. So when you get your LiDAR data, it looks like a point cloud, which is what you see here. It's irregularly spaced points. And for every point, you have an X, Y, and Z coordinate, which is your location and elevation. The files are generally in LAS format, and they vary in their point density and their accuracy depending on the type of sensor that was used. Generally, LiDAR data that's been more recently collected will have a higher accuracy and a much higher point density, whereas if you look at LiDAR data that was collected in the 1990s, you'll see closer to the 5-meter range of point density and the lower resolution. The main advantages of using LiDAR data for coastal mapping is that it's very highly accurate, it's efficient at mapping large areas, and most importantly, it gives you elevation data. So for features that have very similar reflectance values, such as the different features of a beach, the main way to segment them is using that elevation information that is provided in the LiDAR. So for my project, I had 3 main objectives. The first one was to develop this automated model that would classify the individual geomorphic features of the barrier island. And then next, we wanted to use that model to map those barrier features over several time steps and then analyze change in those time steps And then finally, we want to take that change and correlate it to coastal processes that are known to be affecting the barrier islands. So we wanted to study North Carolina barrier islands, but the North Carolina northern barrier islands are very different from the southern barrier islands. And the main reason for the differences that we see is the underlying geology. So in the north, you have 4 major rivers that are very large and they drain into the ocean, and predominantly quaternary sediment. And this leads to a gentle slope of the topography, which leads to long barrier islands that are far from the mainland, and they're only separated by a couple of inlets, 4 to be exact. In the south, what you have is a few small rivers that drain into the ocean, and it's much older subsurface geology. And what that leads to is a steep slope, and you have short, stubby barrier islands that are very close to the mainland. You can see they hug the mainland, and they're separated by many inlets that move and change over time. So to have a model that can classify across the 2 different kinds of barrier islands and a variety of barrier islands in North Carolina, we selected study areas for both a north region and a south region. In the north, we selected Currituck Banks, which is an undeveloped reserve, and then adjacent to it is this portion of Corolla, which is a developed area. In the south, we selected Masonboro Island, which is again an undeveloped reserve, and adjacent to it is Wrightsville Beach. So for my project workflow, I started with data collection. I then moved on to collect field work, and the field work was to collect ground control points, which will then be used to identify the accuracy with which the model is classifying the barrier features. And then LiDAR data was processed, and it had to be processed because of the irregular point density. We had to process it into a digital elevation model that could be used by the model. And then finally, the most time-consuming part of the project was the model development, and I was lucky enough to start with our already pre-made initial model that was developed by Tim Moss, and all I had to do was optimize a large portion of the parameters and improve the modeling, and then we automated the model so that you could run the model basically using 1 click and entering a few parameters. And then finally, the last step is to run the model on several time steps and analyze change. So for the data collection, LiDAR data was downloaded from Digital Coast Access Viewer, and it was downloaded for 4 time steps for each of the study areas. And as you can see, the data was collected at varying seasons and using varying sensors, and all of that had to be taken into account, particularly when doing the change analysis. In particular, you can see that varying sensors produce a variety of point spacings, which produces different digital elevation model quality, which has to be taken into account when comparing data and looking for change analysis that is actually change versus change that you're seeing due to the digital elevation models being different. Tidal data was collected using the tide station that was closest to the study area. So for the north, we used Duck, and for the south, we used the Wrightsville Beach tide. And all the data was collected from NOAA Tides and Currents. And then additional data was collected for beach nourishment from the U.S. Army Corps of Engineers. Wrightsville Beach and Masonboro are on a 4-year beach renourishment cycle. The North study area had no beach renourishment history. And hurricane data was downloaded from the National Hurricane Center. Moving on to my field work, for each study site, we ran transects perpendicular to the center line of the study area, and the transects were cast at 100-meter intervals. And then we randomly selected 25 transects to make the area more manageable, and those are the ones that you see in red. And the data was collected along the 25 randomly selected transects. So for collection, I used real-time kinematic GPS, RTK, by Trimble, the 5800 series, and I walked along each transect and collected stakeout points. For each point, I collected X, Y, and Z coordinates along with a feature code. So we collected the position of the point and the feature that is located at that point. And that feature is what is compared to the model output to see if the model is correctly classifying the ground features. The goal was to collect 60, for every study area, the goal was to collect 60 features per study area. Or sorry, I'm sorry, 60 points for every feature per study area, which comes out to about 500 points per study area. I was able to achieve that for all the study areas with the exception of Masonboro, and that was because we were interrupted by Hurricane Matthew. After Hurricane Matthew passed, we decided that it didn't make sense to continue collecting because the data is being compared to past data and it wasn't going to match. So moving on to the LiDAR processing, there are several different ways to interpolate LiDAR data into a digital elevation model. Using ArcGIS, we tested 3 methods and decided on one of those. So the first method we tested was the LAS data was converted into a multi-point, and then the point to raster tool was used to interpolate the data. And this created a decent DEM, but it had a lot of holes that were going to be a problem for the model. We then tried the LAS to multipoint and then interpolate using the inverse distance weighted tool. And this created a pretty good DEM, but we saw a lot of over-interpolation. Also, this is a very time-consuming process. So lastly, we settled on converting the LAS points into an LAS data set and then using the LAS data set to raster tool, which also uses the inverse distance weighted calculation or algorithm to calculate the DEM, and that was the best for this model. On developed barrier islands, we had to extract the structures before we could run the model. And I tested several methods for isolating the structures, and finally we decided that the easiest thing to do was use the data already inherent in the LiDAR data. So LiDAR data, especially for more recent years, everything after 2010, it comes already pre-classified with class 6 for all structures. And so when we generate a DEM with just the class 6 LiDAR and generate a DEM with ground elevations, we can create a mask for the buildings and then extract them from the ground DEM, and we end up with a DEM for ground returns without buildings. And this is the DEM that we use as the input for the model. So now finally to the model itself. For developed barrier islands, the model is very simple. We interpolate the DEM. The only inputs that need to go into it is the LiDAR LAS files and a study area. And then we run the model from that DEM, and the only additional inputs are tidal data and the study area oceanfront line. For a developed barrier island, we add that additional step of creating the man-made feature mask, and that allows us to generate that ground return without man-made features. So now I'm going to step you through the workflow of the model, and then after that, each of these boxes I'm going to talk about in more detail. So we take that digital elevation model and we segment the study area. We separate water, intertidal, supertidal, and land. The water is further then segmented using a shore position index to ocean water versus estuarine water. We use a topographic position index, which I will explain in a few slides, to then classify the land portion of the barrier island. And we break it down into uplands, hummocks, dunes, overwash, swales, and channels. After that, the classification looks pretty decent, but it needs to be refined further because it has a lot of mistakes. So we refine this classification using a series of shape index, proximity index, shore position index, and orientation indexes to produce a much better classification, which is combined all together into the final classification. Okay, so segmenting the first portion of the island to separate water, intertidal, and supertidal. This is mostly done using tidal data. So water is everything that is below 0 elevation. Intertidal is everything that is above 0 but below mean high or high water. And supertidal is everything that's below highest astronomical tide but above mean high or high water. And we end up with something that looks like this, where you have water, intertidal, supertidal, land, and then of course on the back barrier similar features. The water is separated into ocean water and estuarine water based on proximity to the oceanfront line of the study area polygon. Next, we classify the land portion of the barrier island using what's called a topographic position index. It was developed initially for mapping mountain areas, and it was first introduced by Weiss in 2001. Essentially what you're doing is you're comparing the elevation of a point to its surrounding points, comparing that based on neighborhood. So if a point is higher than its surrounding neighborhood, it looks like a peak or a high point. And if a point is lower than its surrounding area points, based on that defined neighborhood, it looks like a valley. So higher elevations will come up as positive TPI, and lower elevations will come up as negative TPI. And neighborhoods are defined based on sizes of features. So if you have a very small feature, you want a small neighborhood. If you have a very large feature, you want a large neighborhood. And we optimized this and ran several tests, and ultimately hummocks are small features and they have a small neighborhood, and they're peaks, so they have a positive TPI. Dunes and channels and swales are medium-sized features. They have a medium-sized neighborhood. Dunes are peaks. They have a positive TPI, whereas swales and channels are low portions, and they have a negative TPI. The large areas in the barrier island are the overwashes and the uplands. They have a large neighborhood, and respectively, overwashes are like uplifts, and so they have a positive TPI, whereas the upland areas are relatively flat. When you calculate a TPI, this is an example of a TPI for a 40-meter neighborhood, and you can see where the upper peaks are positive and the valleys are negative in their TPI. And ultimately, when you run the TPI on a barrier island, what you end up with is relatively decent classification of all the peaks and valleys, but there are quite a few mistakes. For example, you see overwash in this area, swales and channels are not separated, and you see hummocks on top of dunes. So it produces a good initial classification, but needs further refinement. So we continue to refine this using that series of position and orientation and shape indices. First, we reclassify the overwashes. So initially, when you get the TPI is run, it classifies some overwashes on the front side of the barrier island, which is obviously not correct. Overwash is all on the back barrier. So we reclassify it using a proximity index to the water, to the ocean water rather. And after this reclassification, we end up with really good results where this is classified correctly as a low point swale channel, and all the back barrier is classified as overwash. Next, we separate the channels from the swales. Channels are very vertical features, whereas swales are very horizontal features. So by running an orientation index, we can select the vertical features and reclassify them as channels, and we leave the horizontal features as swales. So your result looks something like that, where all of the vertical features are classified as channels. And then lastly, we reclassify the dunes and hummocks. So initially, you end up with a lot of hummocks on the front part of the barrier island, and you end up with hummocks on top of dunes where they should not be. So we use a shape index to initially run an initial reclassification. Basically, dunes are oval-shaped and hummocks are circular. So everything that's circular is classified as hummock, everything that's oval-shaped is classified as dune, and then finally, anything that is adjacent to a dune is reclassified as dune. So basically, if it's intersecting a dune, it's reclassified as a dune. If it's not intersecting a dune, it's considered a hummock. And we end up with a pretty decent classification. So to sum all of this up, here's what we've done. We've taken a LiDAR point cloud, we've interpolated it into a digital elevation model, and finally we ran it through this classification model to get a classified barrier island with the different features of the barrier island identified as separate polygons. So let's look at some results. When we classify the Mason-Burrow 2014 LiDAR and we drape it over some imagery, you can see from the image that the classification follows the topography pretty well. So you have dunes in the peaks, and you have swales in the valleys, you have some channels. It follows the imagery relatively well. We ran some calculations using the field work to do an accuracy assessment. And it turns out that the model is doing a really good job in the majority of the features, with the exception of the intertidal zone and the channels. When I looked closer at these results, what I realized was that when we were collecting this data, it was right before Hurricane Matthew, and so the tides were actually higher than usual. And so what appeared like intertidal because it was wet was actually supertidal when you look at the elevations. And so this is an error not of the model, but it appears that this is an error of actually the field work. When you look at the channels, it's a similar issue. So standing on the ground, if you're sitting in this position, it looks like a channel. But the model, and in reality, this is actually part of a larger swale system. And so the model actually more correctly identifies this as a swale. So sometimes when you're on the ground, it seems like it's very hard to distinguish these channels from swales. And so a lot of this misclassification, if you look at it, usually the error is in that the model is seeing it as a larger portion of the swale. If we look at Currituck in the northern portion, the northern study area, you get just as good of a classification where your ridges are dunes, your valleys are swales, you got overwash, and then you've got your upland forest. Running the accuracy assessment, again, the model does a really good job with the exception of supertidal and channel. The issue with the channel is the same thing. Where on the ground, this portion looks like a channel, but in reality, it's part of a larger swale system. So I'm confident that the model is actually classifying this better than I was able to collect the data in the field. The supertidal, again, was an error of field collection. What we didn't see in the field is that the elevation up here increases and then slopes back down as you move to the dune line, and that's a natural swale, which we didn't see in the field. And so the field data was collected too close to the dune and it classified as supertidal in the field, and that's an error on our part during the field work. Lastly, we look at the Wrightsville Beach developed barrier island, and the classification, again, does a very good job of identifying the dunes, the swales, the channels. The buildings are separated. The only problem we see is in the roads, because LiDAR data has no class for roads. And so now we have to reclassify the roads. The model actually classifies them either as overwash or channel, which is actually right because they're depressions. But what we plan on doing in the next step is to use the intensity data that we have with the LiDAR data, and roads have a significantly different intensity from sand, and so we should be relatively easily able to separate the roads using that intensity data. And when we run the accuracy assessment again, we see really good results with the exception of supertidal and channel, which I already talked about. Okay, so summing this all up, what we've learned is that we can produce a model that is automated that can map barrier island features using only LiDAR data as the only geospatial source of data. The model can run on both developed and undeveloped barrier islands, and it can run across a variety of different barrier islands, both in the north and the southern region. And we learned some really valuable lessons about how we should do field work when we collect feature classes. The next step is going to be to process this LiDAR data over multiple time steps, analyze change, and then correlate that change to coastal processes. So I would like to thank my advisor, Dr. Joanne Halls. I'd like to thank my committee, Dr. Hawks and Dr. Goneem. Michael Oakley helped with a lot of the field work, and Kevin Carver helped with all of the field work as well as being amazing at home. The Geological Society of America had donated some money to help fund my field work, so I'm grateful to them as well. Questions? Yes.